and welcome to this video. This is a revision video for OCR and we're going to look through the amount of substance, compounds, formula and equations. So quite a bit in this video. Like I say, this video is for OCR. My name's Chris Harris and I'm from AlleryTutors.com. And like I say, this video is going to look at an overview for revision purposes for these topics here. Now, the PowerPoints that I'm using, they can all be purchased. If you just click on the link in the description box below the video, you'll be able to get a hold of them there. Probably great for revision, print them off. You can use them on your phone. You can supplement, obviously, the revision stuff that you've got already. So it's just another way, another form of revising. And like I say, these are very specific to OCRA, and here's the specification points for the syllabus for this topic, and all the content in here is kind of geared towards these points here. Alright, okay, so let's look at the first bit, which is forming compounds. Right, so ions are created when electrons are transferred from one atom to another, okay? So they attract to each other to form compounds. So here we've got two elements here, okay? We've got chlorine and we've got sodium. Now, to gain a full shell of electrons, chlorine needs to gain one more electron to get a full shell. Sodium needs to get rid of this electron here to get a full shell, which will be underneath this outer shell, okay? And then when they do that, when they give up an electron, they form negatively charged ions. Well, chlorine is a negative charge and sodium is a positive charge, and then they attract each other. So let's have a look. There it is there. The electron goes up the chlorine, and we form two ions that are now attracted to each other. This is called an ionic bond, okay? So opposite charges attract. We call this an electrostatic attraction between a positive and negative ion. Okay, just looking at where these ions come from, if you use the group number, this will kind of help. So all group 1s form 1+ ions, group 2s form 2+, group 3s form 3+, 4s we can just ignore. Group 5s, right, these find it easier to gain 3 electrons rather than lose 5. So that's what they do. They form 3- ions. Group 6 form 2- and group 7 form 1- ions. Here's your molecular ions. So you'll need to know these molecular ions because you're going to see them quite a bit. Hydroxide ions, OH-, nitrate ions, NO3-, ammonium is the only positive one on here, which is NH4+, sulfates, SO4 2-, and carbonates, CO3 2-. You've got to know these molecular ions. You're going to see them a lot when you're bonding them with things, so nitrates and sulfates, etc. Know the charges and make sure you know, obviously, the basic structure of it, like CO3, for example. Okay, so here's your compounds. Okay, and this is how we form compounds. Are formed from these ions on here. Okay, so you also need to know about some of these ions as well. You might see compounds specifically to do these. So zinc ion is zinc 2+, and silver is Ag+. So you're going to see compounds specifically in this year 1 chemistry. You're going to see these ones as well. All right, okay. So we can work out the formula of an ionic compound by using what we call a swap and drop method, okay? So the first thing we need to do is write the two ions. We've got calcium 2+ and NO3-. This is just an example, okay? We swap the charges, so we swap them over like that, and we have Ca-, NO3, 2+. Then we drop the charges. Basically, we take away the negative and the positive bit, and we drop the numbers so they're lower. Obviously, there's a 1 in there, but we don't include it on there. And then we basically combine them and simplify if we need to. Now, because this is already in the simplified form, we've already got the formula here. This is calcium nitrate. Notice the little 2 outside the bracket basically symbolises we've got 2 lots of NO3. Let's look at another example. Ca2+ and O2-. Write the two ions down, swap the charges. As you can see, we've swapped them over. Drop the charges, so we have a 2 and a 2. And then what we need to do is we need to combine the two and then simplify it. Ca2O2 can be simplified to CaO. So that's what you have to do. So always try and simplify it where you can. Obviously, you must have whole numbers, not half numbers. Okay. Salts are an example of an ionic compound. Okay. So these are obviously, salts are ionic. So these are, you'll see salts everywhere. So they obviously are very important. So they can be hydrated with water, or they can be anhydrous without water, okay? So if we look here we've got a sodium ion. This would have come from a salt. And you can see that these are obviously interacting with the sodium ion. Chloride ions will do the same as well. Now, water is a polar molecule. Okay, it has a delta positive and a delta negative bit. Okay, and what these do is this means that different parts of the water molecule are attracted to certain parts of the ionic compound. So, for example, the delta negative oxygen is obviously attracted to the Na plus ion, and the delta positive hydrogens are attracted to the Cl minus ion. So what this is doing is it's effectively trying to interact with the salt ions, with the ions that make up the salt, and this is obviously how water works. Now, water molecules, these can exist as within crystal structures, and we can call this water of crystallization. Okay, you'll see this quite a bit. So for every mole of salt you have, a certain number of moles of water of crystallization, and you'll see formulas written like this: .xH2O. This basically tells you how many molecules of water do we have for every mole of substance or salt that we have as well. So, for example, copper sulfate CuSO4 .5H2O, and basically this means that this salt has 5 moles of water for every 1 mole of copper sulfate, and this is called a water of crystallization. This is basically water interacting with your copper sulfate solution. Okay, and obviously we can calculate the water of crystallization as well, and we can carry out an experiment to work out the value of water crystallization. Basically, it's a really straightforward experiment. All we do is we heat the salt, removes the water from the crystals, and what you get left with is an anhydrous salt, which means salt without water. That's all anhydrous means. Okay, so let's look at this example. 1.88 grams of hydrated calcium sulfate .xH2O. We don't know the value. The X just is a number, but we don't know it. Was heated until there was no more water of crystallization was left in the sample. The mass of this anhydrous compound was 1.13 grams. Work out the value of X, which is the amount of water of crystallization. Okay, so the first thing we need to do is to write out the two molecules involved. So we've got a calcium sulfate bit and we've got a water bit. Okay, so we've got the two halves. Then we have to write the masses of each of the molecules. So the mass of calcium sulfate on its own with no water was 1.13. We've worked that out. The mass of the water was literally, if this was the mass with water in it, and that was the mass without, then if we subtract these two numbers away from each other, we can find out the mass of water. In this case, 0.75 grams of water has been lost. Then what we need to do is divide these by the relative molecular mass, and what we're doing is effectively calculating the number of moles. So the relative molecular mass of calcium sulfate is 136, and the relative molecular mass of water is 18. If we divide these two numbers together, we should get the number of moles to be 0.0083 moles of calcium sulfate, 0.0416 moles of water. Then what we do is we divide all the numbers by the smallest number of moles. So the smallest number of moles in this case is this, 0.0083. So we divide both sides by that number. So we divide 0.0083 by 0.0083, that gets us 1. If we divide this by the same number, we get 5. And then all we do is we say, right, this is basically saying for every 1 mole of calcium sulfate, we've got 5 moles of water. So the water of crystallization is 5. So the value of X here is going to be 5. Calcium sulfate .5H2O. Pretty straightforward. Okay, right, let's look at some ionic equations. Okay, so ionic equations show the ions that are formed in solution, and they show which particles are reacting as well. Okay, so normally acids, bases, and salts, these form ions in solution. Okay, so here's a standard balanced equation of an acid reacting with a base. So this is sulfuric acid reacting with potassium hydroxide. And what we're going to do is we're going to write our full ionic equation underneath this one and basically work out what we've got. So here it is, look. So we split the sulfuric acid into 2 H pluses and the sulfate ion. Potassium hydroxide is split into 2 lots of K plus and 2 lots of OH minus. Potassium sulfate is 2 lots of K plus and a sulfate. And then the water isn't ionic, so we just leave it as it is. So we're only looking at ionic compounds here. Okay, and obviously these ions are formed when they're in solution. So water is just left alone. We don't split that up. Okay, so we've got all our ions here. So when we're looking at our ionic compound, what we need to do is we need to cancel any ions that appear on both sides of the equation. And then what we get is our simplest ionic equation. So you can see here we've got sulfates and sulfates, K plus and K plus. These are all the same, but you can see what we're left behind is H plus and OH minus. So let's get cancelling. There you go. So we get rid of them, and we should be left with whatever's left is our simplest ionic equation, showing a neutralization reaction. H plus ions come from the acid, the OH minus ions come from the alkali or the base, and then what we form is water. The sulfates and the potassium ions are called spectator ions. So these ones here, they don't actually get involved with the reaction, but obviously they are there, but we don't need to worry about them because nothing has happened to them on the left compared to the right. Okay, so in this equation here, in the final ionic equation, the charges must balance on the left and the right. So make sure they balance. Obviously, we can have we can just have H plus OH minus forms H2O. We can have that as well. It doesn't really matter. Okay. So let's look at the mole. Obviously, this is really important. Everything in chemistry and to do with your calculations, well, nearly everything in chemistry has got to do with the moles, okay? So we need to know what this is. And we need to know about this person called Avogadro, because he played quite an important role in this. Okay, so the mole is just something we use in chemistry to measure the amount of substance, hence the name of the topic, okay? We can shorten it to mol, M-O-L. And basically 1 mole of any substance, doesn't matter what it is, whether it's an atom or a molecule, will contain 6.02 times by 10 to the 23 atoms or molecules. This is known as Avogadro's number, and we normally see it written as N with a little a as a subscript. So 1 mole of water contains 6.02 times 10 to the 23 molecules of water, and 1 mole of iron also contains the same number, but obviously this is atoms of iron, so it's pretty straightforward. And obviously from this we can work out the number of particles in a substance. We can use Avogadro's number multiplied by the number of moles. So for example, if we had 1 mole of a substance, it would just be Avogadro's number. So that basically tells us the number of particles in there. So let's have an example. How many particles make up 0.67 moles of ammonia, which is NH3? So the number of particles is Avogadro's number times by the number of moles, 6.02 times 10 to the 23 times by 0.67 moles. That's how many particles we've got. 4.03 times by 10 to the 23. Also, be prepared to rearrange this formula as well. Okay, obviously we've written it down as number of particles, but it could get you to work out any number of these. Okay, so let's look at the mole in terms of mass and MR, okay, which is the molecular mass. So the number of moles can be calculated from mass and MR, or it could be AR. Here's the equation. Now you've got to know this one really. So the number of moles is mass in grams divided by the MR or the AR, atomic mass or molecular mass. Okay, so this is ideal for things like solids. So calculate the number of moles of 23 grams of gold. Very nice. Okay, so we give your answer to 2 significant figures. So the number of moles is mass over AR. Okay, mass is 23 because you're using 23 grams of gold. The AR of gold is 197. Okay, so the relative atomic mass. Number of moles is 0.12 moles, and this is given to 2 significant figures. Okay, so make sure you give your answer to the appropriate degree of precision. Basically, look in your question. If you have any 2 of these components, any of these, then you can use it. So look in your question, look at the numbers you've worked out. Do you have any of these? Any 2 of these, and you can use it. So you might have an atomic mass, obviously you work that out from the periodic table, and the number of moles, you can work out the mass of the substance. If you have the mass and the number of moles, you can work out the AR. So anything like that. And also, like with any equation that you'll see on here, be prepared to rearrange it. Okay, so let's look at the mole in solutions. So them ones were mainly for solids when we're using a mass, or anything that's measured in mass in grams. So this one is for solutions. So the number of moles of a substance in the solution can be calculated from concentration and volume. Here's the equation here. So number of moles, concentration in moles per dm cubed times by the volume. The volume's got to be in decimeters cubed as well. Quite often they give you it in centimeters cubed, so you'll have to convert. So like I say, so how you would convert is you divide by 1,000 to get it into decimeters cubed. So they give you it in centimeters cubed, divide by 1,000, or what you can do, and this is what you're going to see a lot in this PowerPoint, all you have to do is take your number that you've got in centimeters cubed and just add times 10 to the minus 3 to the end of it. This means exactly the same as divide by 1,000. Okay, So let's look at an example. Calculate the number of moles of 200 centimeters cubed of 0.35 moles per dm cubed of HCl. So the number of moles is concentration times by the volume. So concentration is 0.35 times by 200 times by 10 to the minus 3. The number of moles is 0.07 moles. So all we're doing is taking the concentration, taking the volume, and there's my times 10 to the minus 3. The reason why I've put that on the end is because our volume is in centimeters cubed. So to get into decimeters cubed, I've to go times by 10 to the minus 3. That means the same thing as divide by 1,000. So you'll see where I've got that from. Okay. And obviously, again, look in your question. If you have any two of these components here, any of them, you can use this equation. So look in your answers. If you've got a concentration, a volume of something, you can work out the number of moles. And then you can use that moles to work out the mass in the previous equation that you'd seen in the previous slide. So you can interchange these equations and you will be expected to be able to do that as well. And also, like with any of them, rearrange the formula. You've got to know how to be able to do that as well. So make sure you're prepared to rearrange formulas if they need you to. Okay, the gas one. Okay, so this is for gases. Now, gas is a bit strange because they occupy different volumes, different amount of space, depending on the obviously depending on the temperature and the pressure of it. So the number of moles in a specific volume of gas. So we use this equation, PV equals nRT, and we call this the ideal gas equation. Now you've got to know the standard units for this. You've got to be really vigilant in these questions. Pressure is P, always measured in pascals. If they've given you it in kilopascals, you must convert to pascals. Volume is in meters cubed, okay? Make sure you're able to convert to meters cubed. I'll show you how to convert units as well. N is just the number of moles, that's mole. R is what we call a gas constant. They'll give you this in the exam. It's 8.31 joules per Kelvin per mole. And the temperature is measured in Kelvin. Again, if they've given you it in degrees Celsius, you must convert to Kelvin. Okay, so let's look at an example. Calculate the volume in centimeters cubed of 0.36 moles of a gas at 100 kilopascals and 298 Kelvin. So we've got PV equals nRT. Rearrange this and we get V equals nRT over P. Okay, the volume is 0.36, we use the volume, is 0.36, which is the number of moles, times by 8.31, which is the ideal gas constant, 298 is in Kelvin, that's the temperature, divided by, now the pressure, look, 100,000. Don't put 100, because we've got to convert to pascals, so it's 100,000 pascals. Volume is 8.91 times by 10 to the minus 3 meters cubed. But look, the answer, the question said we need to work it out in centimeters cubed. So what we've done is we've taken that number and multiplied it by 1,000,000, and that gets you the volume in centimeters cubed. Now, if you're not sure why we've done it in 1,000,000, I'll show you on the next slide, but just bear with me for 2 moments. Okay, so important things though, just before I show you this, is when we're using the ideal gas, you should use the units above. Make sure these units are standard units. Make sure you can rearrange it as well. You've got to be prepared to rearrange it. The gas constant you'll be given, so don't worry too much about that, 8.31. Standard conditions for this reaction is 298 Kelvin and 100 kilopascals. So make sure you're able to recall these standard conditions. Okay, so let's look at these units, because units are quite important here. It's just a little way of trying to explain how these units work. Now you can see what here, I've got 3 different types of dimension here. 1-dimensional units, 2-dimension, 3-dimension. So 1 dimension is just a line, okay? Now if we want to convert to meters to decimeters and decimeters to centimeters, we use this unit quite a lot, decimeters, or decimeters cubed, should I say, in chemistry. Now we don't really use it in everyday life, so it is important to know where it fits with the rest of them. So basically, a decimeter means decade, like a tenth of a meter. So a decimeter is just 10 centimeters, that's all it is. And we've got 10 of these in a meter. So that's why to go from a meter to a decimeter, we multiply by 10, because we have 10 of them in a meter. Going from a decimeter to a centimeter, cent meaning century, like 100. So 100th of a meter is basically, there's 10 centimeters in a decimeter. So it's times by 10. Now obviously, if we're going the full way, like I say, we've got 10 decimeters in a meter, 10 centimeters in a decimeter, and 100 centimeters in a meter, effectively. So we should know that bit. Now, if we are going for the whole way, you can see if we're going from meters to centimeters, what we have to do is multiply by 100 because we've got 100 centimeters in a meter. Okay, now this is fine for one dimensions, but obviously in chemistry we don't use one dimensions. So we're going to show you how we work out to get to volumes. So basically for every dimension we add a 0 from the previous dimension. Okay, so you'd see here, this little number here tells you we've got 2 dimensions because this is an area. So let's have a look. So you'd see here, to convert from meter squared to decimeter squared times by 100, all we've done is added a 0 onto the end. There it is. And we do exactly the same here. Now, that's the extra dimension. There's the extra number there. Going from meter squared to centimeter squared, we just do 100 times 100, which is times by 10,000. So if I want to convert meter squared to centimeter squared, we times by 10,000. Obviously, if we go backwards, you're just dividing by the same number. Okay, obviously the important thing is volume in chemistry. Add an extra 0 on there because we've got an extra dimension, look. So now we're multiplying by 1,000 to go from meters cubed to decimeters cubed. Multiply by 1,000 to go from decimeters cubed to centimeters cubed. Okay, look, there's the extra dimension. There's the extra 0. And basically to go from meters cubed to centimeters cubed, we do 1,000 times by 1,000 because we've got 2 steps here. That's times by 1,000,000. And that is effectively where we get the million from, times by 1,000,000. So obviously just divide by the same number if you're going backwards. Okay, so let's use equations to work out the masses of things. Now obviously you need to know state symbols. You're going to get these quite a lot in your equations. So S stands for solid, L is a liquid, G is a gas, AQ is aqueous, which just means that anything that's dissolved in water. So really kind of look out for these. These are going to be pretty important. Okay, so balanced equations, we can use these to work out the theoretical mass of something. So let's have a look at an example. Calculating the theoretical mass from an equation. So how much calcium oxide can be made when 34 grams of calcium is burnt completely in oxygen? So the first thing we need to do is write down our equation and balance it out. So we've got calcium reacting with oxygen, forming calcium oxide. Make sure it's balanced as well. There's our state symbols, solid, gas, solid. Then what we have to do to work out the theoretical mass, then we basically work out the MR or the AR of the species involved. So because this is only talking about calcium oxide and calcium, we can ignore the oxygen bit. And we write these masses in grams. So the relative atomic mass of calcium is 40 times 2, because we've got 2 of them, is 80. And then the relative molecular mass of calcium oxide is 56 times 2, or formula mass, 56 times 2 is 112. So basically what we're saying is that 80 grams of calcium will give 112 grams of calcium oxide. Now this is theoretical, okay? In a perfect world where you're not losing any product, you get 100% reaction, this is how much you should get. But the problem is we want to know, we don't want to know what 80 grams of calcium, we don't want to know that. We want to know how much of this is made when we burn 34 grams of calcium. So all we have to do is change this number to 34. And that will tell us how much calcium oxide we produce. So the first thing we're going to do is we're going to divide the calcium side by 80 to find 1 gram. Then we're going to multiply by 34 to find 34 grams. And we're going to do exactly the same on the calcium oxide side. So let's go for it. So 80 divided by 80 is 1 gram. So that tells us what 1 gram is. And then multiply by 34. And obviously that will tell us what 34 grams is. I'm going to use these numbers here and use them to do exactly the same on this side to work out how much does 34 grams of calcium give us for calcium oxide. So for 1 gram, it's 1.4 grams. So 1 gram of calcium will produce 1.4 grams of calcium oxide, again divided by 80, multiply by 34, and that will tell us our final answer. So 34 grams of calcium will produce 47.6 grams of calcium oxide. And it's as simple as that. Now, this is the theoretical mass. It's really useful, this particular method, for working out yield, percentage yield, because you're going to need to calculate a theoretical mass in order to work out a percentage yield. Okay, so this is, in theory, how much calcium oxide we can produce. Okay, so we're going to use equations to work out the volumes of gases. Okay, so balanced equations can be used to work out the volume of a gas. So we're going to calculate a volume of a gas from an equation. So for example, what volume of hydrogen is produced when 12 grams of potassium reacts with water at 100 kilopascals of pressure and 298 Kelvin. The gas constant, remember, is 8.31 joules per Kelvin per mole. So first of all, we write out our equation and we balance it. So there it is there. This is 2 lots of potassium react with 2 molecules of water, forming 2 molecules of potassium hydroxide and a molecule of H2, hydrogen gas. Notice our state symbols: solid, liquid, aqueous, gas. This is the amount that we're going to work out. Then we have to do is work out the number of moles of potassium. So we work out the number of moles. Moles is mass over AR of potassium. So this is going to be 12 divided by 39. Okay, because it's the mass of potassium. And that's going to give us 0.31 moles of potassium. Okay, so what we can do, we can work out the number of moles of this substance here. Once we know the moles of one of these, we can use the molar ratios here, the 2s and 1s in front of them, and we can use that to work out the moles of any one of these substances. And once we know the moles of that substance, we can work out quite a few things. So that's exactly what we're going to do here. We're going to use the equation to find out the molar ratio. Now, there's 2 moles of potassium react to produce 1 mole of hydrogen. Look, it's a 2 to 1 ratio. So the moles of hydrogen is 0.31 divided by 2. 0.155 moles of hydrogen is produced. So because we know the number of moles, if we go back here, we need to work out the volume of hydrogen. So let's go for it. PV equals nRT, because it's a gas we're using. Rearrange it to get V equals nRT over P. So number of moles, ideal gas constant, temperature and pressure. So we know the number of moles is 0.155. We've just worked it out here. Ideal gas is 8.31. We know the temperature is 298 because we've been told there. And the pressure is 100 kilopascals. Convert that into pascals, 100,000. So the volume is 3.84 times 10 to the minus 3 meters cubed. And that's the volume of hydrogen gas produced. So it's as simple as that. So we're basically into using the mass equation for moles, and we're using ideal gas equation. So we're using both of them in the same question. But you can see how they work together. Okay, empirical formula. So this is the simplest whole number ratio of elements in a compound. So this is pretty important. So let's look at an example. A compound contains 23.3% magnesium, 30.7% sulfur, and 46.0% oxygen. What is the empirical formula of this compound? Okay, so let's work through a worked example. First thing we have to do is write out all the elements involved. We've got a magnesium, we've got a sulfur, and we've got an oxygen. Then we write out the percentages as masses. So they've given us the percentages of each of the elements. I've taken them percentages and I've just put grams on the end of them. Then we divide these by the relative atomic mass, and what we're working out is the number of moles. So 23.3, the relative atomic mass of magnesium is 24.3, relative mass of sulfur is 32.1, and oxygen is 16. So we've divided these two numbers and we get these here. This is just the number of moles. Then what we have to do is divide the numbers by the smallest number of moles. So if you look here, the smallest number is 0.96. So we divide all of them by 0.96. And here are our answers. We get 1 magnesium, 1 sulfur, 3 oxygen. And then we write our formula. Empirical formula is MgSO3. Now, you might look at that and think, well, that's a bit strange. It doesn't look, might not look complete. Sometimes these empirical formulas don't look complete. Okay, so you've got to kind of have faith in your calculations effectively, because you might get some which look a bit strange. But we can use this empirical formula and we can use it to work out the molecular formula as well. So all we have to do is work out the MR of the empirical formula that we've just worked out and divide it by the MR of the molecular formula that they would have given you. Okay, and then we can use this number to multiply all the atoms in the empirical formula. So we can have Mg2S2O6, for example. So basically we're working out what the multiplier is, and we'll multiply everything in the empirical formula by whatever that number is, because they could get you to do that in the exam. Okay, so let's have a look. More empirical formula. So simplest whole number of ratios in an element. Okay, now this one's slightly different, because actually we've now got a combustion reaction. So a hydrocarbon combusts completely to make 0.845 grams of carbon dioxide and 0.173 grams of water. What is the empirical formula of the hydrocarbon? So all we've got here are just combustion products. So it's similar, but you've just got to think, there's one little extra step that we need to think about here. So instead of elements at the top, we've now got our combustion products, carbon dioxide and water. So we write these as the headings at the top. Then we write the masses of each molecule. We've been told about how much carbon dioxide and how much water we've got there, and there's your masses. Okay. Then we're going to divide each of them by the relative molecular mass of each. So the relative molecular mass of carbon dioxide is 44. Relative molecular mass of water is 18. Now, if we put them in our calculator, we should get 0.019, 0.196. Now this is the number of moles of carbon dioxide in water. Now this is where it gets a little bit tricky. Okay, 1 mole of carbon dioxide has 1 mole of carbon atoms in. Okay, so the original hydrocarbon that we've burnt here must have 0.019 moles of carbon atoms. The only place where the carbons have come from to make carbon dioxide is in the actual hydrocarbon. So because we know the number of moles of carbon dioxide, this is the same number of moles of just carbon in the carbon dioxide. So now we know the number of moles of carbon. Now if we come on this side, 1 mole of water has 2 moles of hydrogen. Okay, so because we've got 1 mole of this has 2 atoms of hydrogen per molecule of water. So the original hydrocarbon must have had that number of moles times by 2 times. Okay, so this is 0.0192 moles of hydrogen atoms in the original hydrocarbon. Okay, this is the tricky bit. You've got to make sure you kind of be able to link the number of moles of this to the number of moles of atoms in the original hydrocarbon. Okay, so the carbon in the carbon dioxide and the hydrogen in the water can only come from the hydrocarbon. Okay, so what we do is we then use them numbers and we divide them by the number of moles of C and H atoms by the smallest number of moles. So the smallest number of moles was 0.019. Okay, so just about. So we divide them both by the small amount and we obviously get a 1-to-1 ratio. So the empirical formula of this hydrocarbon is CH. Now this is what I mean. It looks a little bit odd when we just see it written like that because it looks as though it doesn't look like a formula at all. But that is the empirical formula. Remember, it's the simplest whole number ratio. Okay, so look at percentage yield. So percentage yield is the actual yield divided by the theoretical yield times by 100. Okay, so remember we looked at the theoretical yield last time and we said, right, we needed to know how to calculate the theoretical yield. Well, theoretical yield is the amount of a product produced assuming no products are lost and all reactants react fully. So we showed you that bit already with the 3-step divide to find 1 gram, multiply to find all. That step you would use to work out the theoretical yield. In this example, I'm just going to give you the theoretical yield just to show you how to use this equation really. So in a reaction involving the complete combustion of calcium, 32.6 grams of calcium oxide was produced. Theoretical mass is 47.6 grams. Now this is just an example showing you how to use the equation only. Don't worry too much about the numbers here. So calculate the percentage yield of this reaction. Okay, so obviously you have to calculate the theoretical mass yourself. Again, I've just picked a number just to kind of show you how it works. But the percentage yield is actual yield divided by theoretical yield times by 100. So all we do is you take the actual yield that we've made, 32.6, divided by the theoretical yield. You will have calculated this on your own. This is just an example number, times by 100. The percentage yield, 68.5% in this case. But the theoretical, the actual yield, you'll always get in the exam because obviously you can only get this from actually doing the practical. So pretty obvious really, I suppose. Right, okay. So yeah, the other thing is remember that yield is never 100%. It is virtually impossible to get a reaction to have 100% yield. You lose some of your product when you're transferring it from beaker to beaker. Not all of your reactants would have reacted. You may have lost some product if it was a gas. It might have escaped. Loads of things like that. You might have had impurities in there which have obviously reacted. So you've got a few reasons why you can't get 100%. So as long as you know that, obviously we try to get as close to 100% as possible, but that's about it. Okay, atom economy. Right, atom economy is how efficient a reaction is. Okay, so atom economy is the molecular mass of desired product, what we're wanting, divided by the sum of the molecular masses of all products times by 100. Okay, so let's look at an example. Iron oxide, Fe2O3, can be reduced using carbon or coke to make pure iron and carbon dioxide. Calculate the atom economy of the extraction of iron. Now, obviously, iron is our desired product. So let's bring up our equation here. There's iron oxide, reacting it with coke, and that forms iron and carbon dioxide. So that's our equation. Make sure it's balanced as well, because that's really, really important. So the atomic mass of the desired product, okay, iron is 55.8. Because we've got 2 of them, okay, we have to multiply it by 2. So it's 2 times 55.8. And the desired product, atomic mass of the desired product is 111.6. So that's the this bit here, molecular mass or atomic mass. We've done the top bit. So now what we have to do is the sum of the molecular masses of all the products So all the products, 2 times 55.8 plus 1.5 times 12 plus 16 plus 16, that's your carbon dioxide. That adds up to 177.6. Now we do, stick it into your equation, 111.6 divided by 177.6 times by 100 gives us an atom economy of 62.8%. Okay, so we need to know, just finally, the importance of atom economy. Why do we bother? Well, quite a few things. It tells you how efficient a reaction is, so it is actually really important for chemists. So companies will try and get reactions that tend towards 100% atom economy. High atom economies means that the raw materials are used efficiently, so this is a lot more sustainable and we're not wasting raw materials. High atom economies produce a lot less waste, and so they benefit the environment, so we're not polluting the environment with harmful pollutants. And a higher atom economy means you get less byproducts, so you don't need to spend loads of money separating the products from your desirable ones that you want, which could be energy intensive, which would obviously cost money and could be bad for the environment as well. So that's pretty much it. That's just an overview of this part of OCR specification. Like I say, you can see the little tiles in there. If you just click on the little circle in the middle, you can subscribe to my channel, and that'll be really great. Also, just a reminder, you can buy these PowerPoints as well. If you just click on the link in the description box for this video, and you'll be able to find them there. That's it. Bye bye.